Imagine if solar panels, the ones we see everywhere, could actually grab more sunlight, turn it into power way more efficiently, and just become, well, stronger without taking up more space. Sounds almost too good to be true, right? But some really cutting-edge stuff is making it happen. And today we're doing a deep dive into exactly that. We've got this fascinating document, a patent application, that's really pushing the limits of solar tech.
That's right. This deep dive, it's all about a specific innovation for what you might call next generation solar cells. We're talking perovskite and tandem cells, specifically an idea from Hanwha Solutions Corporation. We're going to unpack their recent patent application, US 2LOD 250185445A1. It just got published June 5, 2025. And it gives us a real window into how companies like Hanwha are engineering solar to be, well, even better.
Okay, let's get into this then. Our mission today. Figure out what this patent tells us about where solar is heading. We want to look at the clever science behind it, the precise engineering involved, and really what this kind of subtle but potentially powerful change could mean for the actual power we get from the sun. It's a deep dive into a pretty specific detail, but one that could have a big impact. So most of us were familiar with the standard silicon solar cells. They've done amazing things, really kickstarted the whole renewable energy transition in many ways. But like any tech, there are limits, right? You can only squeeze so much efficiency out of them. They do a good job, sure, but the sun throws a whole spectrum of light at us, and silicon's only good at converting certain parts of it.
Exactly. Think of silicon like, I don't know, a fisherman with a specific size net. Catches a lot of fish photons, in our case, but only the ones that fit that net perfectly. To really get the most out of all the sunlight, researchers have been looking beyond just silicon. And that's where these materials called perovskites come in. People often call them next-generation energy sources. They're showing huge promise. Perovskites offer potentially really high power conversion efficiency, and they might even bring down manufacturing costs, which is, a big deal for getting solar everywhere. They're like a new kind of net, maybe, that catches a wider range of photons. But they haven't been perfect. They've had some challenges, particularly with staying stable over the long term and not losing efficiency. It's something researchers are constantly working on, though, with new innovations.
Right, so we've got these really promising materials, perovskites, but they need some work. And this is where the whole tandem cell idea comes in, isn't it? Sort of combining the strengths, like stacking nets, maybe?
Exactly, you nailed it. Tandem solar cells are a really elegant approach. You literally stack different types of solar cells. Usually it's a perovskite cell sitting right on top of a traditional silicon cell. The perovskite layer up top is designed to grab the high energy light, the blue and green photons, and it lets the lower energy red and infrared light pass straight through to the silicon layer underneath, which is better at absorbing those. This kind of multi-layer approach lets them capture a much, much broader slice of the sun's spectrum. It helps overcome the efficiency ceiling you hit with just one material. You can potentially get much higher overall efficiencies this way. It's all about making the most of every single photon. Now, here's the fascinating bit. Even with these really clever tandem designs, there's still this subtle challenge. You actually lose some light within the internal layers themselves, specifically in something called the electron transport layer, the ETL. You'd think these layers would be perfectly clear, right? But even a tiny bit of unwanted light absorption there adds up. It steals photons that should be making electricity. And this is the specific problem Hanwha Solutions is targeting in this patent, making sure every possible photon gets used.
Huh. That is subtle. Light getting absorbed where it should. My first thought is, how do you even fix that? It sounds so tiny, but critical. How are they engineering around this internal photon leak?
Yeah, and this is where the cleverness really comes in. The core idea in the patent is this novel graded thin film. They're using it as the electron transport layer, the ETL, though potentially for other layers too. So instead of just a standard uniform layer, think of it more like a meticulously designed window. Its chemical makeup, and therefore its optical and electrical properties, actually change gradually from one side to the other. Not a sharp jump, but a smooth transition. For the ETL specifically, this graded film, it gradually changes its chemical binding state. From the bottom part, the side facing the incoming light, to the top part. And the key insight is this. The lower part of the layer is engineered to absorb less light compared to the upper part. So more light gets through that critical bottom section to the active layers below, while the upper section is still really good at getting the electrons out efficiently. It's like a dual-purpose design, optimized for both getting light through and getting electrons out.
Okay, wow. So it's not just one material, it's like a gradient, changing its job slightly as you go through its thickness. That sounds incredibly precise. What materials are they actually using to create this this chemical gradient.
Yeah, gradient is a good word for it. The patent goes into detail using tin oxide, SNO, as the base material. They describe making this thin film where the composition gradually shifts from tin monoxide, SNO, towards tin dioxide, SNO2, as you move through the layer. Essentially, the amount of oxygen in that very thin film increases bit by bit from bottom to top. You can actually see diagrams of this in the patent figures showing this SNOS layer transitioning. And the reason this is so smart is that tin monoxide, the SNO part, is naturally more transparent to lower energy light than tin dioxide, the SNO2 part. So by having less oxygen at the bottom, it lets more of that useful light pass through to the perovskite and silicon underneath. Then, as the oxygen increases towards the top, it becomes better at the electron transport job. It's all about minimizing those wasted photons while maximizing the electrical current you get out. And that's absolutely crucial for pushing the cell's overall power conversion efficiency higher.
That is a really sophisticated idea, a layer that morphs its properties across its thickness. But no, okay, how? How on earth do you make something like that with such precision? It sounds incredibly delicate.
It absolutely is delicate and highly controlled. This is where the manufacturing method becomes just as important as the material itself. The patent specifies using atomic layer deposition, or ALD. ALD is pretty much a state-of-the-art technique for this kind of thing. It gives you atomic scale precision. Think of it like building a wall, literally one atom-thick layer at a time. That's the level of control we're talking about. It ensures they get that gradient exactly right. The patent even shows the ALD cycle in figure 3. It's basically this repeating four-step dance. First, you introduce a precursor gas, like a tin source. It sticks to the surface. Then you purge, get rid of any extra gas floating around. Next, you introduce a reactant, in this case, an oxygen source. It reacts with the stuff stuck to the surface, forming just one atomic layer of the film. And finally, another purge to clear out byproducts. You repeat this cycle over and over, and the key, the really crucial part, is carefully controlling the flow rate of that oxygen source. By tweaking that flow, they can precisely control the ratio of SNO to SNO2 being deposited in each cycle. That lets them build up the film layer by atomic layer, gradually changing the composition to create that perfect gradient they want.
So by fiddling with knobs like the oxygen flow rate, I think they mentioned TDMA-SN and oxygen flow rates, they can basically sculpt this layer at the molecular level.
Yeah.
Tuning its properties depth by depth.
Molecular sculpting, yeah, that's a great way to put it. That fine-tuning creates the graded effect, making the properties shift smoothly. And there's another big plus here for manufacturing. The patent points out they can do this ALD process at pretty low temperatures, like 150 degrees Celsius or even less. That's a really big advantage because high temperatures can damage the other delicate layers already in the solar cell. Doing it cooler makes the whole process potentially cheaper and more reliable.
That low temperature part is definitely a win. Less energy, less stress on the materials. Okay, let's picture this whole thing. Can you walk us through the stack layer by layer? What does one of these solar cells actually look like with this new graded film inside?
Sure. If you look at figure 2 in the patent, for a single perovskite cell using this, you'd typically start with your glass substrate, the base. Then you've got your transparent conductor, usually ITO, indium tin oxide, that's the anode where current leaves. Then maybe another transport layer, they mentioned nickel oxide, Mylonkux. Then comes the star. The wide bandgap perovskite layer itself, they specify 1.69 electron volts, good for grabbing high energy light. After the perovskite, another transport layer, often C60 fullerene. And then comes our innovative ALD SNOX graded layer we've been talking about. On top of that, you'd put indium zinc oxide, IZO, then an anti-reflective coating, ARC Life, to help suck in more light, and finally the metal contact on top, the cathode, usually silver, AG, to complete the circuit. It's like a very carefully made sandwich, each layer doing its specific job. And what's really neat is the versatility. The patent also clearly shows this working in a tandem cell, that's figure 4. You basically take that whole perovskite top cell structure we just described, and you place it right on top of a standard silicon bottom cell, which has its own electrode on the back. So it proves this graded ETL idea isn't just for perovskites alone. It can boost those high-efficiency tandem cells, too.
Right, makes sense.
Yeah.
And while they focused on tin oxide, SNO, you mentioned it's not only limited to that, correct? The patent sort of opens the door to other materials for this grading trick.
That's right. The patent claims are broader. They cover using various metal oxides, different tin oxides, zinc oxides, indium oxides, potentially others, even combinations. So there's flexibility there for future work. But yeah, their main focus and where they show the really compelling data in this patent is definitely on that tin oxide SNO to 10O2 system. That's where they've clearly demonstrated it works well.
Okay, the data. The
Yeah.
proof is in the pudding, right? Or the power output, I guess.
Yeah.
What kind of actual performance boost did they measure? Did this fancy atomic level grading make a real tangible difference?
Oh, yeah, a very tangible and pretty impressive difference. The data is right there in figures 6 and 8. They ran experiments using different oxygen flow rates during that ALD step, like 20 centimeters, 30 centimeters, 60, 90. Remember, changing the flow changes the gradient, tunes the film's properties, and the results were significant. For example, they made a perovskite cell using a 30 centimeter oxygen flow for that graded SNOx layer. It hit a power conversion efficiency of 14.39%. And the fill factor, which is another measure of quality, was 73.88%. Now, compare that to a cell made with just a 20 centimeter flow. That one only got 11.69% efficiency and a 61.96% fill factor.
Wow, wait, so going from 20 to 30 centimeters, just tweaking that one layer's gradient gave them almost, what, 2.7 percentage points more efficiency?
Yeah,
And nearly 12 points higher fill factor. That's actually a huge jump for just optimizing one internal layer.
it really is a substantial leap in solar cell terms. Each percentage point gain is a big deal, especially when you scale it up. Think about a massive solar farm. That extra 2.7% efficiency means generating significantly more electricity from the exact same area. Or you could generate the same amount of power using fewer panels, less land. That translates directly to lower cost materials, installation, everything, and a smaller environmental footprint. Innovations like this are absolutely key to making solar even more competitive and widespread. It's a real game changer. And they backed it up scientifically, too. They used something called XPS analysis, X-ray photoelectron spectroscopy. Figures 5 and 7 show this. It's like a chemical fingerprint. It confirmed that the chemical binding energy shifted through the film, proving the oxygen content was gradually changing exactly as they designed it. It directly links their precise manufacturing to those improved performance numbers. Hard evidence.
So pulling this all together, this deep dive into the Hanwha patent, it really shows that even in a field like solar, which feels pretty mature, there's still so much room for clever innovation, right? It's not always about brand new physics, but refining things with smart engineering.
Exactly. By engineering this graded thin film for the ETL, using that super precise ALD method, Hanwha is tackling a really fundamental, maybe easily overlooked problem: light getting lost inside the cell. It's a nuanced detail, for sure, but as the data shows, fixing it has a really significant measurable impact on how much power you actually generate. These kinds of detailed improvements are crucial as we try to push efficiencies closer and closer to the theoretical limits.
It's just amazing how advanced materials science and these incredibly precise manufacturing tools can unlock whole new levels of performance. And for all of us, this kind of progress means, well, better, more efficient solar panels, more clean energy from the same sunlight. That's a huge win all around.
Absolutely. Pushing the boundaries like this, step by careful step, gets us closer to that future where solar is even more powerful, even more affordable, just everywhere, which does make you wonder.
What other kinds of material science breakthroughs, maybe things we haven't even thought of yet beyond these tandem cells and graded films, could unlock even more solar potential? How much further could we really push this technology to transform our energy world? It really makes you think.